So let me introduce you Dr. Wang, and he's a professor of biomedical engineering at Tulane University. He heads the multi-scale bioimaging and bioinformatics lab at Tulane University, and the laboratory has three themes: fundamental research on multi-scale signal and image representation and analysis, multi-scale bioinformatics analysis from organ and tissue levels to molecular and cellular levels, bioinformatics and human genomics and the cytogenetics. So this talk is based on two recent publications in different IEEE transactions, very good journals, very good papers, congratulations. Interpretable Multimodal Fusion Networks Reveal Mechanisms of Brain Cognition, that's one. And another one is Deep Collaborative Learning with Application to the Study of Multimodal Brain Development. We all here work on deep learning in some capacity and neuroimaging. Somebody works on multimodal neuroimaging, so this is very, very relevant to most of the work of the team, and everyone's connected. Welcome here. Welcome, Dr. Wang. Can you please go on from here?
Okay. Thank you very much for the invitation. So I have collaborating with your center, for many years, since you guys were in Mender Research Network, and we continue work on many joint research projects. So I'd like to share our recent work.
Can you go full screen, please?
Okay. So I'd like to share our recent work on interpretable deep learning models. To be honest, I'm not a big fan for deep learning, and I was hesitated about entering the deep learning world until the last 3 or 4 years ago, and I realized deep learning does have many advantages. So we began to work on some of the research problems and compare the deep learning model with linear models. And we found that there are many good things about deep learning models. So let me begin with a general introduction to the project we are currently interested in. As you know, the current era is precision medicine. From my point of view, it is really driven by multi-scale, multi-modal genomic and imaging data analysis. So for a complex disease, we usually collect many types of data, multi-omics from the DNA sequencing level to epigenomics and to the proteomics. On the other hand, for brain imaging, you can also collect the the imaging data from different modalities and at different scales, and those data have different formats, different resolutions, and sometimes the data points are missing, so they are quite heterogeneous. Okay. So in imaging genomics, so the goal is to correlate the multimodal brain imaging and also multi-omics, and find their associations, and furthermore we can integrate those imaging and genomic data and use them to detect significant biomarkers that are related to disease, or use those biomarkers in particular the interaction network between different omics or between different brain regions, or even the interactions between imaging and genomic data, and use them as biomarkers to make a prediction or make a diagnosis. By the way, feel free to stop me if you have any questions or comments. So I realize this is not a formal talk, so it's a good forum for us to exchange ideas. So I'd like to hear your comments when I present my slides. So there are a lot of challenges for integrating multi-scale, multimodal brain imaging and genomics. So first, those data are collected from different platforms, or even from different labs, where often we have to do data harmonization, right? So we have a joint research projects across 4 states, including with Calhoun at your institute, Tony Wilson at Nebraska, and Julia at the Meng Research Network. So those data are very complicated. So we have to do lots of normalization in order to do subsequent analysis. So secondly, those data are of different types. If we consider disease types, where often we have binary types of data, right? And for genomic data like SNPs, they are discrete. We usually use 0, 1, 2 to represent different numbers. And for phenotypical traits, they are continuous. So this raises a lot of challenges for representing those mixture type of data. So when we consider the model design, so we have to consider those factors. For example, shall we use a linear model or non-linear model? As I mentioned at the beginning, I was not a big fan for deep learning. One of the big reasons is that there is a lack of good interpretability for deep learning model. There are a lot of tuning parameters in the deep learning that we needed to tune, right? And by training, I was a mathematician. I always favor the simple, beautiful model, yet powerful, to solve a challenge. Okay. So the deep learning model is more, complicated, and they are good at representing nonlinear features, but on the other hand, it's very challenging to interpret. So I will, propose some solutions in the next 2, research projects that I'm going to show. Okay, and also for correlation analysis. So you can use simple, Pearson correlation to find the relationship between different brain regions. And in the last few years, we also proposed the distance correlation, which shows more powerful solution to identify more complex relationship between 2 data types, such as imaging and genomics. We also use kernel CCA, to identify complicated relationship between 2 or 3 data types. And in current data integration or correlation analysis, so a pairwise or 2-way correlation is commonly studied. It's not that challenging anymore, right? It's more challenging to study the correlation across 3 or more types of data. So very often we are facing with more than 3 types of data for analyzing. So it's very challenging to analyze multi-way correlation and data. And for data integration or fusion, and my group has worked with many different models, including multitask learning, non-negative matrix factorization, and statistical graphical models. And we found that those models have pros and cons. Let me see why my slide cannot move. Okay. Okay, so those are the models that my group has developed in the last decade. So in my group, we have biomedical engineers, statistician, mathematician, computer scientist, and many of my graduate students or postdocs have a training in mathematics. So we work with mathematical people to propose novel ways to address the challenging in data integration. For example, we propose to use projected distance correlation, multiple graphical models, graphical Fourier transform, tensor decomposition, also alternative diffusion map to perform nonlinear dimension reduction. And those models have pros and cons. And now we work on causality modeling and also the deep learning model. And those are the sophisticated models which give us more advantage in identifying the nonlinear relationship between the imaging and the genomic data. So besides the model development, so we work with Wings and also other collaborators to perform rigorous validation by testing the model using different data sets from different labs. So this way we can promote the reproducible research. So your group is a pioneer in data integration and correlation analysis, and we know the CCE model is a very powerful way to find the correlation between two heterogeneous data. For example, here we have the genomic SNPs and also the imaging data. And if we perform simple correlation analysis, we cannot find their relationship. However, if we project both the genomics and imaging data into another variant and find their maximum correlation, we were able to identify the association between the genomic SNPs and the imaging brain or imaging network. So the CCE model has been used in statistics and many other fields for many years. And mathematically, it can be formulated as the maximization of the following, object function. So, this approach can detect the cross-modality correlations, and can also be used for, feature selection or dimension reduction. So there are many kind of, variants, such as, joint, CCA, class-specific, CCA. However, the CCA model cannot be linked with, phenotypical, data. So in the deep learning framework, people proposed deep CCA model. So the idea, is quite, similar. Unlike the linear, CCA model, here we use multi-layer, neural network or deep network to project, the data x1 and x2. So here, f1 and f2 represent the two multi-layer neural network. In the simple case, if we just have, one layer, right? Or take f1 and f2 to be a matrix that reduced to be a linear CCA model. But for the deep CCA model, f1 and f2 can be more, complex nonlinear functions. So at the output layer, we find their, maximum, correlation. So this way, we can detect the complex relationship between the two data types, x1 and x2, after they are represented using the nonlinear, multi-layer network or nonlinear function f1 and f2. However, like the like the linear CCA model, so the deep CCA model still cannot link the detected features with phenotypes. Then we have kerr-regularized learning, or multitask learning. So the idea of kerr-regularized learning is to combine the CCA model or correlation model with regression model. So we know the regression model is a good way to link the two imaging and genomic data, x1 and x2, with phenotypical trace y, right? Are you able to see my, pointer?
Yeah, we can see it.
If not, okay, good, yeah. So here, is a very simple, linear version of the kerr-regularized learning. So the first term, is a regression term. So we use both, genomics and imaging data to fit the phenotypical trace y. In other words, we minimize the fitting error between y and x1 and x2. We use alpha to denote regression coefficients. So on the other hand, we can perform CCA analysis, right, by projecting x1 and x2 into theta 1 and theta 2. We know theta 1 and theta 2 represent the two variants. And in addition, we can enforce constraint like the following term to couple the regression and the correlation together. So this way we can combine the regression and the correlation, and we can also add a hyperparameter to make a balance between regression and the correlation. So the co-regularized regression model or co-regularized learning model has the advantage of combining the regression model and correlation model, which can overcome the overfitting issue. And this is one type of multitask learning. Okay, so in statistical, analysis, so they call this as collaborative regression, which was proposed in 2014 by two statisticians, Cross and Tibishwani. And we know Tibishwani also proposed LaSalle, right? And they use collaborative regression to couple the regression model with correlation model. So in the following formulation, so the first term is simply the CC term to consider the cross relationship between x1 and x2. The last two terms are the data fitting or regression term, and we can use three tuning parameters, B1, B2, and B3 to have a trade-off between data fitting and data correlation. Okay, so this was the collaborative regression, and we have improved this model by using different coefficients to represent regression and correlation respectively. And for this model, we have used them to find the curve expression between brain imaging and genomics, which was published in 2017 in actual medical imaging. And for this model, it still has weakness for not being able to detect the complex relationship. So to this end, we propose a model. We name this as deep collaborative learning model, or DCL model. And for this deep collaborative learning model, we use the following ideas inspired by both the linear collaborative regression and the deep CCA model. So first, we use a multi-layer neural network to represent our input data, X1 and X2. So at the output layer, we have Z1 and Z2. And unlike the linear collaborative regression or CC model using F1 and F2, we can represent the complicated interrelationship within different data sets X1 and X2. So at the output layer, we add a collaborative learning layer. So in this layer, we find the cross-modality correlation between Z1 and Z2. Okay, so this way we have the deep CC model, right? We can have the advantage of deep CC model by finding the relationship, complicated relationship across two data sets. At the same time, we link the two output, Z1 and Z2, with a phenotypical variable Y. So we add another, data fitting to link the output with the label Y. So this way, we can couple the deep CCA with the regression. So this can give us a lot of advantage. First, so this model can identify the complicated relationship across two modalities, X1 and X2. In the same time, right? With the same modality, using the multi-layer neural network, we can find the interactions between different data points with the same modality. Okay, so at the output layer, we can link the two nonlinear representation with phenotypes. So this can have the potential to improve both the regression and correlation. So we call this as deep collaborative learning. Let's check the mathematical formulation. Oops. Okay. So mathematically, we can use the maximization of the following object function. So the first term, we project the nonlinear representation Z1 and Z2 into U1 and U2. And we use the trace to denote their relationship. So we find the two projection warrant matrix U1 and U2 to mix their correlation to be maximized. So the last two term is a data fitting term. Okay. So by minimizing the fitting error or maximizing the negative of the minimum error, we can have a good fitting. We know Z1 and Z2 are the nonlinear representation of two data modalities, X1 and X2, right? And we use beta 1 and beta 2 at the output layer, to perform, regression with phenotypical variable y. Y can be continuous or can be discrete if we wanted to do, data, classification. So there are, several, parameters that we needed to identify. Beta 1 and beta 2 are the regression coefficients. U1 and U2 represent, the correlation variance. So we also needed to find the nonlinear, multi-layer neural network Z1 and Z2, right? So we can simplify this object function with a number of mathematical manipulation to be the maximization of this object function. So eventually we needed to find the multi-layer neural network of Z1 and Z2 to represent these two network. Do you have any questions?
Anyone?
So in the same time, just like the linear CC model, we enforce the constraint on U1 and U2 using the similar constraint. So in order to solve this optimization problem, we needed to find the gradient with respect to Z1 and Z2. After we find the gradient, we can use mini-batch stochastic gradient descent to train the model.
I have a question here, Ivan. Why do you even need to do manual differentiation here? You can just use AutoDiff that takes the gradients through your neural networks. You don't do the manual differentiation for your deep learning models. Once you constructed the full model, you can just give it to, I don't know, PyTorch, TensorFlow, any automatic differentiation package, and they will implicitly compute this for you. Is this exercise just so you needed something specific from this expression, or why did you have to derive this?
Okay, yeah. You can use a numerical, approach, numerical algorithms, or use some, available, package, to do the, gradient, calculation. But, if you have the, the explicit formula, this can make the, the, stochastic gradient descent approach, to converge easily.
It's the same. Somebody raised their hand. Can you just maybe, if you had a comment, just speak up?
Sorry, this is Jean.
Hey.
Yes, hi.
Yeah, nice to see you again here. Just quick questions, because I mean, I like your idea to combine the deep neural with this collective learning. Right, exactly this the cost functions here. I was confused because the collective learning that you are trying to do the gradient descent or minimize based on the coefficient U and the beta, and your deep learning is try to change Z1, Z2. Look like the two segments are training on different ways. Maybe I'm mistaken some understanding here.
Yeah, so to maximize this, object function, we perform sequential, optimization by, finding, beta 1, beta 2, followed by UI and beta 1, beta 2, UI, U2, followed by Z1 and Z2.
So you have to train like 2 steps. The first, because your collaborative learning is training for beta and U, and your deep neural network is training on Z1, Z2. So it's like every iteration you have to train separate 2 steps?
Yeah, so from my understanding, we do, yeah, those, sequential, steps.
Okay, so the fixed one, train another one, the fixed one, train
Yes,
another
yeah,
one.
yeah.
I see.
We take alternative, steps to find the, those, models, parameters. Yeah.
Okay, then that makes sense because I know that there's a 2 different set of parameters. Okay. Yep. Thanks.
Yeah. Yeah. So this is a computational expensive procedure, and in order to apply the mini batch stochastic gradient descent, we often need to find the gradient, right? And so we have a explicit formula to compute the gradient. So this can make the calculation more accurate. And once we find the gradient, we can combine with backpropagation, right, to pass the gradient from one layer to another layer. So this way we can train the model. And if you check our paper in IEEE Biomedical Engineering, in the appendix, we show the detailed procedure for deriving those gradients.
Yeah, sorry, I didn't check the paper first.
Okay, yeah. So so my student, Wenxing, did this work. He has a very strong, background in applied and computational math. So,
yeah,
he did a lot of, lengthy, procedure of calculations to figure out the, the explicit formula for computing the gradient.
Yeah, but my comment still remains. You don't need that explicitly. AutoDiff engine will do this for you. And also, unfortunately, I checked Rogers is not on the call. We have a very good tutorial that any student can learn how to compute gradients like that by hand, by executing AutoDiff by hand. And it's not difficult actually. You can arrive at this formula using AutoDiff rules, but manually, and you will get. It's in appendix of one of Rogers's papers. But yeah, like basically you can optimize. My understanding is you optimize or maximize the objective end to end. So you could just write it as a formulation and AutoDiff engine will do that.
Okay,
we can go
good,
offline, but yeah, you don't need this gradients.
That is good to know that part. I think for Professor Wang's work here is because he has 2 sets of parameters, which is different because the first set is the goal of the CCA part, the regularize the CCA part. That is
well, that's here, right?
The second part, that's the second part of this. So if you one slice before, you can say it's here, right? This one, there's 2 sets of parameters right now. The Z1, Z2 is for the neural network part, but there didn't list out another parameters, U and the beta, U1, U2, and beta 1, beta 2. That is another set of parameter. So for
yes, that's fine. That's what we do in deep learning. It's one layer is one set of parameters, another layer is another set of parameters, and so on.
No,
It's
that's a difference. That's a difference here. You cannot put into the one, because you have to fix one and change another one.
You
Can I join from my experience?
Okay.
So I understand like about CCA, and so basically you can reformulate all this objective as a metric learning. You just define a metric. You can define cosine similarity as your metric, and input in the function like optimization objective. And this projection, linear projection in CCA, you can just swap by linear layer in neural network. So basically, we don't have to like consider this linear projection in CCA as a part of CCA, because what CCA does is just optimize, like it's optimizing metric which you define like dot product here. You can define cosine similarities there, and it will do better with deep learning, just because when you use exact solution for CCA, you do SVD decomposition, you will have to put additional like coefficient, which will make the solution numerically stable. But in a stochastic process, like with stochastic gradient descent, when you're training the model, it's easier to break the solution. Like it's really hard to optimize this objective. So I think we have to consider like the CCA as a maximization of the metric, and you can define this metric, for example, by cosine similarity, and it will do the same, but it will do better in deep learning scenario. But like this solution, CCA solution, is from 2013, and there wasn't like powerful after differential models like in PyTorch right now, and we just have to disintegrate parts. Like CCA, it's not just like when we have to project specifically and then compute dot product. It's a just projection. We can do it with linear layer, and then we do just metric learning like dot product. We can do bilinear form or any other kind of computation. We can normalize it by vector norm. So this is more like 2013, when like we didn't have powerful techniques, and we have to derive all the gradients, and we have to define exact solution. Just from my experience, that I compared CCA with cosine similarity metric, and cosine similarity metric works much better. And you can also measure like similarity between the presentation you get, and it just like the problem here is just this solution works for 2013, and now we can kind of disintegrate CCA to smaller pieces. Like we can use for projection just linear like layer in neural network, and for dot product we can define like cosine similarity, and it will work beautifully. It just there are like better ways to do it, I think, right now.
Thanks,
But
Alex.
I don't say like you're not. I'm not saying you're not correct. I'm just saying that we have to like disintegrate these pieces, because we have like choice. We can disintegrate objective on projection, and they can be linear or non-linear, and then we just maximize the metric itself. And maximizing metric, you can also choose like different metric learning methods. Like you can use margin loss, you can use any other loss. But like it's better to stay in high level what we want to do. Like as I understand from collaborative learning, we just want to learn, for example, using regression private components of the modality, and then we also constraining it with shared information using CCA. I think it's better to disintegrate all the small pieces and don't take this method as a whole. Yeah,
Okay.
this
Thanks
is
for the comment. Yeah, any other comment? Okay, so let me go to the next slide. Okay, so I want to show you, some examples for applying the, deep collaborative learning model. And we know, our brain functional connectivity network can be considered to be, brain fingerprints. And using the fingerprints, we can link our brain connectivity network with cognitions and behaviors, and we can use the brain network fingerprints to make predictions. And so we want to apply this model, to study whether we can, extract the significant, brain connectivity network patterns and use them to distinguish, different, cognitive groups, with different, ages, genders, or behaviors. And there was an interesting study in Nature. I think many of you are aware, when we study the, the intelligence of individuals at different, ages, they show different, patterns. So at the early age, there is a significant, difference between their, connectivity or connectome, distinctiveness. But at the older age, such a gap become smaller. So one of our, project is to make use, multi-paradigm, fMRI to link the brain connectomes with behaviors and cognitions. Because deep learning needs a large set of data for training and testing. So we use PNC data or Philadelphia neurodevelopment cohort study, to test our model. We also have the David Cobb data, but currently, for that data, we only have about 200 samples, which is small for training the the deep learning model. So we decided to use PNC data to do the testing. We have nearly 1,000 subjects for the young people from age 8 to 12, and for each subject we have the resting state fMRI, the MBAC or memory test fMRI, and emotion fMRI. So like many other work, we first perform pre-processing to correct the motion, and also get rid of other pairs by performing the normalization or smoothing operation. So after that, we ran our deep collaborative learning model for the combination of two types of data, such as resting state and MBAC memory, resting state and emotion task, or emotion and memory task. Even with nearly 1,000 subjects, we still, needed to do some, data augmentation. So we just, use a standard, procedure for data augmentation to generate, some images, such as, performing, image rotation, reflection, or scaling. So this way, we can make our, data sets to be larger when we train the model. Okay. For training set and testing set, we perform before we perform the augmentation. We do the separation first. So here is the result. When comparing the deep collaborative learning model or DCL model with other conventional models, including CCA model, kernel CCA, deep CCA, the logistic regression, the collaborative regression, which is a linear version of the deep collaborative learning. And we found, using our deep collaborative learning model, we can get a highest, accuracy in classifying two age groups. So here we divided the data into, two groups: the pre-teenager group for those kids with the age from 8 to 11, and young adults with the age 18 to 22. So we found that, using our new, deep collaborative learning model, we get the highest, accuracy. So this is for the combination of resting state fMRI and in-back fMRI. This is for the combination of resting state and emotion fMRI. The last one is the combination of in-back and emotion fMRI. So we get a consistent result in having the highest accuracy in classifying the two age groups. So we also perform classification on two groups with different IQs. So for the IQ, we use WRT score, which is a very popular metric to quantify the IQ. So we divided the population into a high IQ group and a low IQ group. For the low IQ group, so their WRT score is between 55 to 89. Well, for the high WRT group, so they have a score from 114 to 145. Again, for each pair of combination of fMRI, tasks, so our deep collaborative learning model can deliver the highest accuracy, which is around 85. So it's a little bit lower than classifying the age group, but they are consistently higher than using other model. Finally, we wanted to illustrate why our deep collaborative learning model can give the best accuracy in classifying different age or cognitive groups. So we just use TSNE to project the data into different clusters after performing those different approaches. And you can see the CCA model cannot, separate the two groups. Here, we have young adults and the children or pre-teenager group. And in the cluster map, you can see it's very difficult, to separate the two groups. Similarly, for kernel, CC and deep CCA, since they are, designed for correlation analysis, not for, classification. So we were not able to use them as, a good, feature selection or dimension reduction, to separate different groups. So using collaborative regression can do things better, but still, there are many overlaps between the two clusters. And, for the deep collaborative learning, you can clearly see, the separation between the two clusters or two groups. So which demonstrates that the deep collaborative learning is a better way to represent, two different groups based on, imaging, multimodal, imaging data. We're not going to, stop there, and we are more interested in, identifying the significant features that can contribute to the good classification. So in other words, we want to interpret this model. As we know, deep learning has a, obvious, problem in its poor, interpretability, especially, for a multi-layer, deep learning model. And we often, consider, deep learning as a black box, right? It's very difficult to know which feature are, more important. Okay, and so it's very difficult, to identify the, the feature sets based on the deep learning model. So we simply use famous, or popular, conclusion sensitivity analysis to help us to interpret the features. So the idea is we can artificially remove certain features and see whether the final classification accuracy will drop. If that classification accuracy drop, we will consider this as an important feature. Okay, so after running our deep collaborative learning, we identify significant, functional, brain connectivity networks. So we wanted to pick out which subsets of the functional network are more important. So we use the, inclusion sensitivity analysis to help us the interpretation. So here we identify 11 cyber networks. As you can see, if we do not remove any cyber network, for the age group classification, we can have 95% of the accuracy, right? If we remove semi-motor network or SM network, so you can see the accuracy drops significantly to be around 65%. So in other words, we consider the semi-motor network to be an important feature. So using a similar approach, we also identify the other 10 sub-network. For example, the default mode network, as you can see, if we remove the default mode network, the accuracy will drop to 60%. Okay. So at least, we use this approach. We are able to interpret this network. But this model still has difficulty in providing the interpretability for identifying, significant, brain regions, or provide or p-value, for ROI, level. Okay. So, to that, end, we propose another, model, which I'm going to discuss next. And you all have the link, to this paper. And so it was performed by Wenxing, who is currently working as a postdoc at the University of Pittsburgh. And he's going to move to Boston to work for a pharmaceutical company. So as I mentioned before, for our deep collaborative learning model, a big problem is the poor interpretability. To that end, we recently proposed our gradient cam guided, convolutional collaborative learning model. And for this model, instead of using deep collaborative, instead of using multi-layer neural network, we change the architecture to be convolutional network, because in convolutional neural network, there are some good approach to help the interpretability, like using gradient cam. Okay. So here is our framework. Again, let's consider genomic SNPs and brain functional connectivity networks as the input. And at the beginning, and we use brain tissue specific SNPs to do some pre-selection. So after that, we feed this pre-selected SNPs or genomic data into a one-dimensional convolutional network. And similarly, for the brain connectivity network, we use a two-dimensional convolutional network to represent the features. So after we obtain the one-dimensional feature map or the two-dimensional brain connectivity feature map, so we add a collaborative layer. In the collaborative layer, we find the correlation between the two feature maps. In addition, we link with phenotypical trace or class map. So we add another layer or gradient cam. So we know the gradient cam can be used to identify significant features. For one-dimensional SNPs, we can use a gradient cam to identify significant SNPs, and also this feature can be class specific. So we can, identify the features specific, to different class. Like high IQ or low IQ group. So they may have different, SNPs. And similarly, we can use gradient cam plus the guided propagation to identify, significant, brain connectivity networks. Again, these feature maps are class specific. So I'm going to use a example at the end to illustrate the advantage of this new architecture. Any questions?
Yes, I have a question actually. So you have used GradCam to compute feature attributions, but I would like to know that how you actually validated that these features are really important.
Yeah, so I'm going to get to that point, how to use gradient cam to select, class specific features. Okay.
Yeah, I understand that you have used GradCam to identify class specific features, but my question was how we can validate that these features are really discriminative. For example, in occlusion sensitivity, you have measured classification accuracy drop as a proof, as a validation that these features are important. But in case of GradCam, how did you validate the identified features?
I see. So your question is how to use gradient cam to identify important features, right?
No.
That
My
can
question is
lead
not
to
that.
the better or worse, classification.
Yeah, my question is how we can validate the identified features by GradCam. I mean that, okay, the GradCam can give us important features, but how can we prove that these features are really important?
I see. How to prove? Okay. Yeah. So I will use an example at the end to illustrate how to validate the features selected. So that's always a a very good question. How to validate the features.
Mm-hmm.
Yeah. So we can perform cross validation. We can link with other types of data to validate the features. Okay.
So
Yeah.
we actually did similar type of work, and we actually proposed some validation framework. So we use these identified features and some random features, and then we classified another independent model to see how they perform based on these identified features and random features. So we use that kind of validation technique in our approach.
I see. Okay. Yeah. Yeah. It's good to learn your story. Okay.
I'm sorry, I have a question.
Okay. So let's look at the formulation of this gradient cam guided collaborative learning. Okay. So I like the deep collaborative learning, and this model use a convolutional network architecture, and also I like the the deep collaborative learning model. So the loss function is designed which is independent on the batch size, So in let's consider the two classes scenario. So the first term, as you know, is data fitting term. So after performing the convolutional network, we have two output, H1 and H2, right? So then we can use this to do data fitting or link with the class label Y. So we here Y represents the class label. So here we have two classes, so we can consider Y to be 0 or 1. So therefore we use this term to do class label fitting. So the second term is a cross entropy term, which consider the cross relationship between the two output layer, H1 and H2. So this is a loss function used in our CCIR model. And we can easily extend this loss function to multiple classes like this. Okay. So here, if we have multi-model data sets like m number of views or m number of modalities, and also C classes. So we can use the following loss function to represent such a model. Okay. So our goal is to minimize such a loss function in order to get a optimal representation of the two input data. Okay. Yeah. Oops. So our goal is really to interpret this model. Yeah, this multi-layer, this deep collaborative learning model, and we know that the CM model is very popular, but it's very challenging to interpret this model, because this model rely on many factors, such as the use of the convolutional kernel, the number of layers, the number of nodes, and the selection of activation function, right? And also it depends on the normalization procedure. So there are any question? So yeah, so there are a number of parameters or factors that can impact the accuracy of the convolutional network. Earlier, people use camel approach, to find the the best feature. So the idea is, for the CAM-based approach, so the idea is to find the ways that can combine those, different, features. So at each, convolutional, layer, we have a, feature map, right? So in order to, find the optimal, features, we needed to, you know, find the weights that can combine those feature maps and check, you know, which combination of the feature map can deliver the best result. Okay, but you know, CAM has its own, you know, problem because when we use CAM or class activation map based approach, so we have to, you know, retrain the model when calculating the weight, and also, you know, we needed to add an additional, you know, layer, classification layer after the feature map layer. So it is not a, you know, end-to-end, you know, model. And when we identify the weights, we needed to add an additional layer and need extra, you know, training time. And very often, because we break up the, you know, the architecture, you know, the accuracy of the, you know, classification will drop. Therefore, you know, people propose to use gradient CAM. Let me move. Oops. So here is the, you know, the idea of the gradient CAM. So for gradient CAM, we can calculate the weight and activation map using the following two, you know, formulas. So we calculate the gradient by, you know, finding the, you know, gradient of the prediction score YC with respect to each feature map FK. So FK, you know, represent the case, you know, feature map. We can simply, you know, take the gradient of the, you know, prediction score with respect to the, you know, the feature map, followed by, you know, error rigging and pooling operation. So this can, you know, simplify the, you know, calculation. And because of the, you know, the error rigging and pooling, the resolution usually drops. So when we calculate the, you know, the map after, you know, taking the weighted, you know, combination of the feature map, we needed to do upsampling. So this way, we can recover, you know, the high level or high resolution feature map. Okay. So when we go back to the original resolution, we can combine with back propagation, you know, to move the identified, you know, gradient from one layer to the next layer. And when we perform the back propagation, we can add some, you know, constraint. For example, we need a request, you know, this gradient to be positive. So this way, we can identify the important features at the, you know, pixel level. So this is just an illustration for identifying the important, you know, pixels, image pixels that can, you know, give a high classification accuracy. So unlike the, you know, the deep collaborative learning model, right? We use, you know, on collision sensitivity analysis, we cannot identify the features at the ROI level or even at the pixel level. But using gradient cam, we can identify the features at the pixel level or at the high resolution level. So this gives us some advantage for using gradient cam in combination with guided propagation. Again, so let's look at an example for using our gradient, guided collaborative, layer network to integrate, brain connectivity network and, genomic data. Next slide. Okay. So again, we apply this model to the brain development study using Philadelphia neural development cohort study. We have nearly 900 subjects with the age from 8 to 21 years old. First, we use existing biological, database like the GTEx to, select the SNPs that are, brain tissue specific. So this can, reduce the computational, complexity, and also for the, brain functional connectivity network. So we use power template based pixelation to focus on the connectivity network in 264 brain regions. We have a 264 by 264 functional connectivity matrix. So these are the the two inputs to our convolutional collaborative network. Okay. So here, we use our CCR model or collaborative convolutional network to classify two IQ groups, the low IQ group and high IQ group. So we use WRT score, or you can also use fluid intelligence, right, to quantify the IQ. And so we know WRT score is a good measure of the comprehensive cognitive ability, including reading, comprehension, math skills. So we use we divided the data sets into training, validation and testing. So the validation set is usually used to identify the the tuning parameters. So here is the result. So we first, use this model to classify the low and high IQ group, and you can see using our gradient cam guided collaborative convolutional network. We can get the highest accuracy and also a slightly higher sensitivity and specificity when compared with other conventional models. such as multi-layer perceptron network, SVM, decision tree random forest. But more importantly, we can identify significant, functional connectivity maps. So here you can see on the left, it is functional connectivity map for the low IQ group. On the right is a functional connectivity map for the high IQ group. On top of the figure is based on the gradient cam. On the bottom, it is a gradient guided gradient cam based approach. And so using the gradient guided gradient cam, so that the matrix is more sparse. In other words, we can pick even more significant feature maps. Okay, so using this gradient guided CAM approach. So we identify 3 significant hubs. They are responsible for visual processing, object recognition, and word processing. And those 3 hubs show different density of connection between the low and high IQ groups. So on the left figure, it is correlation between different brain networks for low IQ group, and on the right one, it is intercorrelation between different brain regions for the high IQ group, and you can see they have different number of connections on those brain regions. We performed a literature search and confirmed those significant ROIs or regions or brain regions. Also, for the SNPs, since this model is class specific, so we were able to identify the SNPs that are significant for low IQ and high IQ group. And based on the the SNPs, we also identify the corresponding genes and show the difference between the low and high IQ group in terms of genes. And furthermore, we perform gene enrichment analysis and identify the significant pathways between the high and low IQ groups, and those pathways can find evidence from the existing study, which can further confirm the cognitive behavior difference between the 2 groups. So this work was again conducted by my former PhD student Wenxing. He actually contributed to several interesting models, including multiple sparse, CC models to the recent, deep collaborative learning models. So let me summarize my, recent work. So we do feel, the deep collaborative learning model can have many advantages, in particular for, uncovering the complex relationship, across different data modalities, and also within each data modalities. And the interpretability, is a significant challenge, but it deserves further research. And so my group is also part of this survey paper. So and forward to more collaboration with your group. And so we have done a lot of good collaborations in the past, and I look forward, to more, productive collaborations in the future. Okay, and you can also, find the source codes on the deep collaborative learning model from our website. And one goal, our, research is to to promote the reproducible research. So, we are happy to, share our codes and work with you guys. So thank you for your attention. Let's stop here.
Thank you very much. Dr. Police had to step out to another meeting, but I'm in charge of stopping recording and save it for later. Thanks for giving this talk.
So, you're welcome to contact me, in case you have additional, questions. So thank you very much for your attention.
Thanks for recording here.